So now we're going to turn our attention to discussing reactive programming, which is yet another of the many paradigms that Java supports. We have a little slide deck here shortly that goes through all the different paradigms and compares and contrasts them, but we'll start by giving an overview of reactive programming. And there are four primary principles that underlie the reactive programming paradigm. You can read about them in the Reactive Manifesto. Apparently, you're not allowed to have a new paradigm unless you have a manifesto, like the Agile Manifesto or the GNU Manifesto or the Communist Manifesto, different manifestos that have been influential over time for better or worse. And we're also going to talk about the benefits and some of the limitations with these principles, because it's not all unicorns and rainbows, as I like to say. So first of all, what is reactive programming? It's an asynchronous programming paradigm that's concerned with processing streams of data and propagating changes throughout the streams of data. And what it does is it composes things together in a manner very much like Java streams that you're familiar with, but it composes asynchronous and event-based sequences using various types of operators. And again, just like streams, these operators can transform and filter the data that flows between the various operators. Ideally, to get the most out of reactive programming, the operators are non-blocking. And that just means that they don't wait for the completion before they go on to the next thing. And we'll talk quite a bit about how that works under the hood. The way that works, in just a quick synopsis, is that the operators are mapped transparently to one or more threads. You can either have one thread or a pool of threads or an elastic pool of threads and so on. And the processing of the events goes to the operators in these pools of threads if you so desire. And the reason for doing this is because the programmers wanted to avoid the overhead of starting and stopping threads. So we have a pool of threads, and then things flow through, and they're mapped accordingly. And you'll see there's a little representation of this that says, represent anything as a data stream that can be created on any thread, functionally transformed and consumed by everyone on any thread. So that's kind of a synopsis, sort of a meme-like synopsis of what reactive programming is all about. Reactive programming is useful for certain kinds of scenarios. So one thing it's very useful for is processing user events. And so you'll see it used in things like Android, where they have stuff like RX Java, and you can actually use Kotlin in a very similar way to react to clicks, touch events, mouse movement. Not really in an Android device, you wouldn't have a mouse typically, but you get the idea, touch events, GPS location signals, and so on and so forth. So all those things can be handled reactively using the mechanisms that are baked into stuff like RX Android, which is an RX Java variant for Android. Another very popular way to use it is responding to and processing latency-bound I/O events, so things where they could block. And here's a nice little picture that illustrates this. So let's say you've got some feed of events flowing in, like a Twitter stream perhaps, and you want to be able to take the incoming events, and you want to be able to filter them, do some kind of analysis to look for sentiment, are people outraged about the latest episode of South Park or whatever, and then you group the results and forward them on to various observers who are subscribed to those Twitter feeds. And the idea here is to be able to handle a large number of events very scalably with the hardware at our disposal. Another way you can use this stuff, which is what we're going to be doing here later in the class, is to communicate between microservices in a modern web-based computing environment, a modern reactive web-based computing environment. And this diagram should look somewhat familiar to you now because we've taken a look at this in a couple of contexts, the most latest one being the quote services example where we had an API gateway. Your assignment 2 also has an API gateway. And so clients, which could be mobile clients or browser clients or whatnot, send requests to this gateway, and then the gateway uses reactive means of communicating between the various microservices, so nothing blocks. And if you get lucky enough to have a fully reactive client, then you have no blocking whatsoever. That sometimes is harder to do in practice for various limitation reasons. Reactive programming is based on 4 key principles. And they are, first, responsive, which means we provide a rapid, or we attempt to provide a rapid and consistent response to users in terms of the amount of time it takes to deliver the results. So the idea is to try as much as possible to have relatively reliable upper bounds, to deliver a consistent quality of service, and prevent undue delay. The undue delay is represented by the hourglass or the spinning wheel. Those are things that you might be familiar with from Mac or Windows that indicate something's taking longer than you might expect. The second principle is resilient. We want the system to remain responsive even if something goes wrong. So if something fails, we want that thing to fail. It's sometimes hard to prevent failure altogether, but the failure of one or more operations shouldn't cause the entire system to come crashing down. So we want things to be able to fail in a very localized and isolated way. The third principle is to be elastic. This is really important nowadays, especially with multi-core environments, especially with cloud computing environments or cluster computing. And you want the system to remain responsive even under varying workloads. So as performance load increases, we'd like to be able to shed load or relocate load or transition load or migrate load to other places to be able to run more scalably, perhaps by using more cores or more computers, which may cost more, but in some situations that's perfectly acceptable. And the phrase for that you may be familiar with is called auto-scaling. So you want to be able to auto-scale your systems to run in larger environments, and then once the peak burst has gone away, be able to scale back down, perhaps costing less, using less cores. And then the final principle, which is a little different than the other three, is being message-driven. So the first three are really about concepts and principles that are generic, like auto-scaling, elasticity, reliability, low latency, those kinds of things, responsive. This is about how we accomplish that. And the idea is to be message-driven, which means we're going to have asynchronous message passing between components to ensure loose coupling, isolation, and location transparency. So this principle is much more of an implementation detail. And we'll talk more about that in a moment. So there's a whole bunch of reactive streams frameworks available now, and we're going to be focusing on one of them. We're going to be focusing on Project Reactor. And there's other ones like RxJava, and there's all these other things here, but we're going to be focusing on Project Reactor, and I'll explain why we're going to be focusing on Project Reactor when we talk about the web-based part of this section of the course, where we're going to be focusing on something called WebFlux, which is a reactive web programming environment. So that's the end of the overview of the reactive programming principles.